Okay, so it's a great pleasure to have Sahand from the IAS who will tell us about cluster state as a non-invertible SPT phase. Please take it away.
Okay. Hello, everyone. So thank you very much, Sakura, and thank you for the invitation to this very nice seminar series, which I'm really learning from. And I hope that I could also have a positive contribution to it today. Okay, so this talk is based on this paper that I did with Shu Hang that we posted on arXiv earlier this month, and is about non-invertible SPT phases on the lattice. And please stop me and ask questions whenever something is not clear so that the talk would be more interactive. Okay. Okay, good. So let me start. Okay, the introduction is that, as is the theme of this seminar series, we know that symmetries are very important for understanding strongly coupled quantum systems, and in particular for classifying gap phases of matter. For example, one could try to distinguish different phases through different patterns of spontaneous symmetry breaking. It could be on ordinary symmetries or even on generalized symmetries. So it could be higher form symmetries, non-invertible symmetries, and in more general categorical symmetries. And in this nice paper, they call it like kind of categorical Landau paradigm, which is a nice name. That I like it. And by the way, I want to apologize that I have a very incomplete list of references. And please don't be offended if I don't include many important work in this talk. And for a complete list of references, please see our paper. So, for example, to distinguish different phases, one example is just ordinary ordered phases, which correspond to order disorder phase transition, which correspond to conventional symmetry breaking. But then we could have topological order, topological phases, which correspond to spontaneous breaking of higher form symmetries. And finally, we could have symmetry-protected topological phases, which correspond to spontaneous breaking of dual symmetries. And this would be the topic of the talk today. So I will explain what do I mean by SPT phases. Any questions? Okay, good. So this is, again, some very incomplete list of references. So some classical papers on SPT phases on the lattice, some references about generalized symmetries, and these works are more closely related to this work, which are about non-invertible SPTs, but there are many other works as well. Okay, so to make sure that we are on the same page, since I think this audience is kind of a mixed audience, so let me just review some synonym for SPT phases in different contexts, depending if you're coming from a high energy point of view, or math, or condensed matter, or quantum info. So in quantum field theory, SPT phases basically correspond to local counterterm, which correspond to different ways of coupling a quantum field theory to background gauge fields. So these are usually depends on some regularization scheme in some short distance physics that in the log distances we usually don't care about, but the relative counterterm between two theories could be meaningful. So this is a QFT point of view. And from the more mathematical or TQFT point of view, SPT phases correspond to invertible field theories, which are just TQFTs whose partition function are phases and have one-dimensional Hilbert space on any spatial manifold. And then from the condensed matter point of view, that would be the focus of this talk, would be symmetry-protected topological phases. And so these are basically phases that are smoothly connected to the trivial phase, but through a path that necessarily breaks the symmetry. So if you forget about the symmetry, they are in the same phase as the trivial phase, but imposing the symmetry, there could be different phases. And finally, from the quantum info perspective, they correspond to short-range entangled states, which are basically the ground states of these SPT phases. And so once you have these short-range entangled states, you could prepare them by some finite depth quantum circuit that we call entangler. And then these entangler, if they're in distinct SPT phases, these quantum circuits, their gates have to break the symmetry. So I will talk about more on this. And so some example, the classical example is a quantum Hall systems and topological insulator, which are even realized experimentally. So topological insulator are some material that in their bulk, they are gapped, kind of boring, but on their boundary, they have some interesting gapless edgements. Okay, so So what are some of the SPT indicators, some of signatures of SPT phases? So if you have some system, how we can tell that this is a non-trivial SPT or not? So the most important signature of SPT phases is the protected edge modes at their boundaries. So basically, if you have this system with some symmetries, and we see that the symmetries on the boundary is realized projectively. So this is in 1+1 dimension, or in higher dimension, the symmetry on the boundary could act anomalously. And in the continuum, this corresponds to the anomaly inflow picture. So the other way to distinguish two different SPT phases is through spontaneous breaking of the dual symmetry. So if we have some system with some discrete global symmetry, we could often gauge these global symmetries if they're anomaly free in this case. And then different SPT phases, which are, it might not be obvious to distinguish them, but after gauging the symmetry, they just correspond to different spontaneous symmetry breaking pattern of the dual symmetries that we get after gauging. So and one idea is to distinguish them through this pattern, and these correspond to the string order parameters I will explain. So these are two main signatures that I will focus in this talk. There's also two other signatures. So one is the one which is more familiar in the continuum, which is a kind of topological response. Basically, we could couple the theory to non-trivial background gauge field A and look at the partition function of this invertible theory that characterizes the SPTs, and we get some non-trivial phases. And microscopically, this corresponds to the symmetry charge of the symmetry defects, but quantized charge of the symmetry defects. I will explain a little bit about it. And finally, there is also the point of the quantum info point of view, which is about the entangler. So if you have these short-range entangled states, they're often related to the trivial state by some quantum circuit, which is called the entangler. And if this state is a non-trivial SPT, this entangler would have a mixed anomaly with the original symmetry. But yeah, so this would be the fourth indicators, but in this talk, I will mostly talk about the first two. Is there any questions so far about terminology? All right, good.
And so this quantum circuit that prepares the SPT state is also invertible?
Yeah, so usually this is assumed to be invertible. Yeah, it's some unitary symmetry that, yeah, that's entanglement, exactly.
And does it is it order related to the order of the symmetry, or it can have any kind of order?
It can have any order. So you assume it's if you want to take it as a symmetry, it's just a Z. So you don't assume any relation for it. It's just a unitary operator. You don't assume anything about it. And then if you classify like the mixed anomaly, assuming this is a Z symmetry, you could kind of give the same classification for the SPT.
Okay, thank you.
Yeah, thanks. Good.
The statement about the depth of this circuit, especially if the SPT has some chiral central charge, say integer quantum Hall phase, as you wrote in the previous slide.
Yeah, so I'm okay. So there is one thing that I didn't maybe explain well enough is that there is a different notion of SPTs on the lattice and the continuum. So for example, in this case, I only consider internal symmetries. So I don't consider chiral states. So I want a state that for getting the symmetry that is only protected by symmetry, not like a chiral phase, which is not protected by any symmetry.
Well, but on the previous slide, you had quantum Hall, right?
Yes, basically, I mean, like spin quantum Hall effect, so which is like the part which is only protected by the U1, not the chiral central charge of it. So I'm assuming some system which has the total thermal Hall conductance is 0. It has only the Hall for
something that might be protected by time reversal and has 0 central charge on the boundary. You have both chiral copies.
Yeah, that's right. Yeah.
Okay, I see.
Yeah, thanks for the question. Any other question? Okay, so the goal of this talk would be basically to discuss lattice Hamiltonian realizations of 1+1 DSPT phases protected by non-invertible symmetries. Okay, so the outline is that I first review the cluster model, which is the simplest example of a Z2 times Z2 SPT phase on the lattice. And then I will discuss its non-invertible symmetry and show that it could be think of as a non-invertible SPT. And then I will construct two other SPT phases which are protected by the same non-invertible symmetries, and then discuss edge modes and other things. Okay, so let me review the cluster model. And so I think maybe not everyone in this audience might be familiar with this cluster state. So I want to make a rather long review of this model. So if you already know this model, I apologize that it would be boring for you. But if you do not, please ask me a question if something is not clear. Okay, so what's the model? So basically the model is very simple. We have the Hilbert space is a tensor product of two-dimensional qubits. So we have L sides, we have a chain of L sides, and we take L to be even. And the Hamiltonian on a periodic chain have this simple form. It's just ZXZ. And so the hero of the story is a Z2 times Z2 symmetry of this Hamiltonian, this cluster Hamiltonian, which is given by the product of the Pauli X matrices on even side and the product of Pauli X matrices on odd sides, which comes with this Hamiltonian. So we have X, Y, Z Pauli matrices at each side. Okay, and this is a exactly solvable model because all the terms in the Hamiltonian commute with each other. So basically you could simultaneously diagonalize them and find the full spectrum and see that, you know, you have a unique gap ground state and the gap is exactly one, independent of system size. So it's kind of, you could say it's almost like a trivial theory. So the claim is that this cluster model is a non-trivial Z2 times Z2 SPT phase, which is distinct from the trivial phase. So what's the trivial phase? The trivial phase has this just paramagnet Hamiltonian, sum of x's, and its ground state is a product state. So we call this trivial state because the ground state has zero entanglement. It's basically you have a bunch of qubits which are completely factorized and decoupled. So what does it mean? What this claim means? So the first fact is that it's a SPT phase. It means that the cluster state should be able to smoothly be connected to the trivial phase without encountering phase transition if you are willing to break the Z2 times Z2 symmetry. But if you want to preserve the Z2 times Z2 symmetry, the claim is that there is no way to smoothly connect the cluster to the trivial state. Okay, good. So now let me show why this is the case. So the first observation is to note that the cluster and the trivial Hamiltonian are related by this unitary operator. Yes, Julian.
Yeah, sorry. Just want to make sure the cluster state. I am familiar with this representation of writing of the Hamiltonian and the symmetry, but I wonder whether there is a different way of presenting this same SPT, but without using the symmetry such that you only X on the even side or odd sides, but such that the Hilbert space, the symmetry will X on the Hilbert space such that it will always be tensor product without specifying. Just you will not distinguish like even or odd sides. Are there different way of presenting this? Does it affect your result? That's what I want to know.
There should be many other ways, but here, if you wish, you could pair each two qubits together, and you view the local Hilbert space as four-dimensional. And here, I don't care about translation, and you only preserve translation by two sides. So from that perspective, everything would be on a single side. But on the top of my head, I don't know other representation of these SPTs, but I'm sure there should be other ones.
Okay.
That's what to say.
Okay, thank you.
Yeah, thanks for that. All right. So the first observation is that these two Hamiltonian are related by this unitary operator, which is a product of the so-called CZ gates, which has this simple formula in terms of Pauli Z matrices, and they have this simple action on local operators. So they send X to Z, XZ, and Z to Z. So here I reminded the Hamiltonian for these two models, and you could easily check that they are indeed related by this V. So this V is called the finite depth quantum circuit, also known as the cluster entangler. So okay, so this unitary tells us that these two Hamiltonian have the same spectrum. So they almost like have the same phase, but we want to do more. We want to smoothly connect the two Hamiltonians together. And this is easy because basically we could take any power of this unitary operator V. So from this way of writing the unitary operator V, we could write it as exponential sum over our local terms. And then we could have this parameter T and change it from 0 to 1. And when it's 0, this is identity. When T equals 1, we just get this V. So basically by doing this, we could continuously, so we have a Hamiltonian evolution and we could, smoothly connect these two systems together, and there is no phase transition because this is just basically a unitary transformation. However, this Hamiltonian evolution given by VT breaks the Z2 times Z2 symmetry because these are Z2 odd, these two terms. So even though they are in the same phase, but imposing the symmetry, this cannot tell us that they are in the same phase. So some remark is that, first of all, this, the ground state of the cluster model is also given by acting V on the product state. And this V create the short-range entanglement pattern in the ground state. So this is some short-range entanglement. And the claim is that this pattern of short entanglement is protected by Z2 times Z2. And one thing that I mentioned before is that this cluster entangler V has a mixed anomaly with Z2 times Z2. So that's one way to see that this is a non-trivial SPT. Basically, acting with V just perform the operation of stacking with SPT. And from the invertible point of view, we have two different, invertible theory point of view, we have two different topological responses. So we could try to basically put these theories in different backgrounds and act with a symmetry operator to get different topological responses. So the trivial theory has a completely trivial response. Its partition function is 1 because the defect here is kind of trivial. And here we get this topological response. This basically corresponds to the fact that the defect of the one symmetry has charge under the other symmetry. But I'm not going to go into the detail.
What is the meaning of this mixed anomaly in this case? Can be understood in terms of a response mixed that involves V, Z2E, and Z2O?
So I will discuss this mixed anomaly in detail later. But it's just basically, for example, if you have some Hamiltonian that has V as its symmetry and also this Z2 times Z2, there would be a type 3 anomaly between these three symmetries.
I see.
So
And is there a meaning of gauging V?
Yeah, so V is some, in this particular case, V is some Z2 symmetry, and you could try to gauge it. And actually, I will make some comments about gauging and all of this later.
Yes.
If it wasn't clear, please ask me again.
Thanks.
Okay. Any other question?
Yeah, regarding the mixed anomaly, is this kind of a, is this a general thing? If I have some SPT with the symmetry and then I have the entangler, there's always a mixed anomaly between the entangler and the symmetry.
Yeah, I believe this is general. Yeah.
Okay, thanks.
But yeah, thank you for the question. But I should say that it's particular mixed anomalies. Yeah. If you classify mixed anomaly and you consider this as a Z symmetry, then that would be a general result. Yeah. Right. So now let me try to distinguish these two phases. So I want to distinguish them by two methods. One is by gauging by different pattern of spontaneous symmetry breaking, and then the other one is by the edge modes. So let me first discuss the gauging. So basically, I want to try to gauge this Z2 times Z2 symmetry and show that the cluster state and the trivial state correspond to two different patterns of symmetry breaking. So then I have to explain how to do the gauging on the lattice. So let me do a very short review of gauging Z2 times Z2 symmetry on the lattice, which correspond to the minimal gauging, and the continuum correspond to the untwisted gauging. So basically the procedure is as follows. So we could start with a Z2 times Z2 symmetric Hamiltonian. And this is not the most general one, but is a quite general Hamiltonian. That is Z2 times Z2 symmetric, quite simple one. So what gauging means? So the gauging corresponds to, it has two steps. The first step corresponds to adding gauge field and then imposing Gauss law. So in this case, we want to add gauge field for Z2 even and Z2 odd, and respectively odd sites and even sites. And this X tilde is the gauge field. So we take this and minimally couple it to gauge field, and we get this H prime here. And basically, to say why this is the case, basically, if you set this to be, if you set this to be -1, this corresponds to inserting a single defect. And the next step is to impose Gauss law, which is given by this relation on even and odd sites. And so you could easily check that this Gauss law commutes with the Hamiltonian. And basically, after imposing the Gauss law, we could rewrite the Hamiltonian in terms of these gauge invariant operators, which describe all the degrees of freedom after gauging.
Sorry,
and in terms of
excuse me, what is Z tilde?
So the gauge fields are X tilde and Z tilde. So basically, we add degrees of freedom on links, on even and odd sides. So we have a single qubit at each side, extra qubit. And X tilde is basically plus and minus 1 is the gauge field, and Z tilde is its conjugate variable.
I see.
Yes. Good. So now, so these are the gauge field, the tilde variable. And now after imposing the Gauss law, everything can be written in terms of this X prime and Z prime, which are the gauging variant operator. And we have this form. So basically, we start with H, we get H prime. And you see kind of the X term and ZZ terms kind of swap. And so all of this can be summarized in a single transformation here, which sometimes called the gauging map, and I call it S gauging. So basically, you could summarize gauging to say that if you have a Z2 times Z2 symmetric Hamiltonian, the Hamiltonian is probably just written in terms of X and ZZs. And the gauging is done by replacing X with Z prime, Z prime, and replacing ZZ with X prime. So in simple terms, you could basically have to do this. And this is the gauging on the lattice. Any question? All right.
Yeah, actually, I have a question. So here you specify this as untwisted gauging. If you wanted to do twisted gauging on a lattice model like this, what about this procedure would change?
Yeah, I will get to it. I will discuss the twisted gauging as well.
Okay.
Yeah, if we can play this. Yeah. All right, so this S gauging is basically on the lattice correspond to kind of Kramers-Vernier transformation separately on even side and odd side up to a translation symmetry, and is basically given by this. And if you apply it to the cluster Hamiltonian and the trivial Hamiltonian, you basically get these two Hamiltonians. It's easy to check. So you see that the cluster is kind of goes to itself, modulo this prime here. So basically, the cluster goes to a symmetry preserving phase, but the trivial phase goes to this kind of this phase, which is a symmetry breaking phase. And so because these two are really different phases, this contradicts, so there couldn't be any smooth path between the two phases before gauging. Because let's say there is the cluster state and trivial states are smoothly connected to each other. Then we could gauge the Z2 times Z2 symmetry and see that these two phases are smoothly connected, which they are not. And I'm using the fact that gauging basically is some topological manipulation which commutes with the RG flow and phases. So this proves that these two are indeed different phases, which correspond to different pattern of symmetry breaking. So furthermore, these two phases, because they are just conventional order and disorder phases, they are distinguished by some local order parameters. And if you track them, they correspond to some string order parameter before gauging. So basically, we get this string order parameter, which for a trivial phase, its expectation value is 0, but in a cluster phase is a constant up to exponential correction. So this could distinguish these two phases even before gauging. So this is the first method to distinguish these two. Any question? All right. So now let me discuss the H.
What happens to this order parameter when you conjugate with that unitary symmetry that takes one Hamiltonian to the other? You demonstrated at the beginning that the cluster and the trivial could be related by just a simple unitary transformation.
That's right. Yeah.
And so what happens to this string order parameter under that unitary?
So this right, I haven't thought about this. So let's see. So V basically sends X to ZZ. So it just includes two Z's at the end.
Yeah, I'm wondering how a unitary transformation can.
Yeah,
Well,
I haven't thought at this point.
Yeah, this X to if it takes a string operator to something wildly different, then I can understand why. Anyway, okay.
Cluster state is self-dual under gauging, right? Both Z2s.
Sorry?
The cluster state is the cluster fixed point Hamiltonian is self-dual under gauging both Z2s, right?
That's right.
So probably the string order parameter should map to itself under such a gauging.
But the idea was that two different phases before gauging, the cluster state and trivial state, are related by V. So the question is how this expectation value changes. I think so there are two string order parameters. One is when J is even 1J is odd, and I think if you act with V, it inserts Z, which has a charge under the other symmetry. So it will change the property of the string order parameter. But I think this is not a good answer. So let me think about it and maybe discuss with you later. Thanks for the question, Greg. All right. Any other question? Okay, so let me discuss the edge moves between these two states. So basically, we could take the same chain with L sides and divide it into two parts and put the cluster state on one half of the chain and put the trivial state on the other half. And we have this Hamiltonian. And so there is one interface around site 1, which is the left interface, and there is another interface around this other site, the green site here, L. So this Hamiltonian is chosen such that it commutes with the original Z2 times Z2 symmetry. So basically, there is some freedom to adding some boundary terms at these interfaces. So here I have chosen one. I have made one choice, but basically you could make any choice as long as you preserve the full Z2 times Z2 symmetry. So this Hamiltonian, again, is exactly solvable. You could solve it. All the terms commute with each other, and it has 4 ground states, which signaling a double degenerate edge mode at each of the 2 boundaries. So we want to argue that these degeneracies are protected by the symmetry. There is no way to lift them by adding symmetric deformation to this Hamiltonian. So the idea is that we look at the action of the symmetry on these 4 ground states or on the ground space. And we see that the Z2 symmetries, the 2 Z2 symmetries are factorized into an action only on the left interface and an action only on the right interface. So basically for the Z2 even, we have these expressions, and also for Z2 odd. So the action factorizes, and we see that there is a projective algebra between the local factors of the symmetry at each of the interfaces. And because this is a projective algebra, this has the smallest representation is 2-dimensional, so this protects the doubly degenerate edge modes at each of the interfaces. And by symmetric deformation, you cannot change these two simultaneously, both of these minus sign to plus signs, because the deformations are local. But the total symmetry still acts linearly. Okay, so this is another way of distinguishing these two phases. Any question? All right, so basically I'm going to take these 2 methods and next up at the end apply to the non-invertible symmetry case. Okay, so with this review now, let me discuss the non-invertible symmetry of the cluster model. Okay, so the first observation is that the cluster Hamiltonian is invariant under this transformation that I mentioned before, but before there was a prime here and I'm ignoring the primes this here. So the idea is that this transformation is not implemented by a unitary operator because this is not an automorphism. For example, if you take the product over all x's, this maps to identity under this transformation. So it's not an invertible transformation. So it cannot be implemented by a unitary operator. And the idea is that it is implemented by a non-invertible operator, non-invertible symmetry. So the claim is that there's a non-invertible symmetry operator D, which implements this transformation in this sense. So usually when we write arrow, it corresponds to conjugation, but this wiggly arrow is correspond to this intertwining action because D is not unitary, and I cannot do conjugation. And the explicit form of this D is given by this, so the T is translation, and D even and D odd are basically the Kramers-Vanier operators on even sides and odd sides separately. They have this explicit expression. Okay. So the other point is that D implements the self-duality under gauging Z2 times Z2, as I mentioned before, is the S gauging. And we know from the continuum that if a theory is self-dual under gauging its discrete discrete global symmetry, it means that it has a non-invertible symmetry. So in this case, this non-invertible symmetry is described by this Z2 times Z2 Tambara-Yamagami fusion category. So we expect that to have this symmetry on the lattice because this model is self-dual under gauging. And indeed, you could check that this operator D satisfies a Z2 times Z2 Tambara-Yamagami fusion algebra. So if you square D and you do the computation, you will find this, and then this algebra, which is a family of algebra of this category. So there are, in the classification of Tambara-Yamagami fusion categories, there are 4 classifications, there are 4 solutions. So 3 of them are anomaly-free and admit SPT phases. And our symmetry should also be anomaly-free, because it acts on the cluster state cluster Hamiltonian, which has a unique gap ground state. So these three categories are known as rep D8, rep Q8, and rep H8. So D8 is the dihedral group of order 8. And the claim is that our non-invertible symmetry is actually described by rep D8. So there are various ways to see it. One way is by gauging the symmetry and show the dual symmetry is D8, or by computing the F symbols from the fusion of topological defects.
So what's the difference between these categories? Is it just the morphism spaces, or I mean, you're writing the tensor, you're writing the simple objects are the same, the
Right.
products of simple objects are the same, but what's different?
Good question, thanks. So they have basically the same fusion algebra, but they are distinguished by two invariants. One of them is the bi character, and the other one is the Frobenius-Shor indicator. So there are two choices of bi character and two choices of Frobenius-Shor indicator. So there are 4 solutions. And these correspond to different F moves. So in this talk, I wouldn't have time to describe them, but I will try to distinguish them by just the pattern of gauging. The character table is the same, but they're kind of, these associators are different. Did I answer your question?
Yeah, I'm getting it. All right, thank you.
Yeah, thanks. Great. So then, because of this, then we could view the cluster model as a SPT phase protected by rep D8 symmetry, non-invertible symmetry. And in particular, we have this SPT state, the cluster state, which is a short-range entangled state, which is preserved by the symmetry D, in the sense that acting with D and cluster, we get 2 times cluster. All right, so this poses 2 questions.
Can I ask something?
Yes,
Hi,
sure.
Sahand. How do I fix the overload normalization of D on the lattice?
So yeah, I fixed it by this relation.
It's just impose the fusion algebra.
Yeah.
Okay, thanks.
In general, it's arbitrary, but I'm just fixing it such that I have this fusion algebra. Yeah.
It's great. Thanks.
Okay, thank you. Good. Any other question? All right. So now there are 2 questions that I want to answer. Is that, first of all, I said that the cluster state is protected by rep D8 symmetry, but is it a trivial or non-trivial rep D8 SPT? And the other question is that are there other rep D8 SPT phases? So I will argue that the first question is kind of don't make sense. I cannot define the notion of trivial versus non-trivial SPT phases for non-invertible symmetries. But then I showed that actually there are 2 other rep D8 SPT phases, and I will describe them. All right, so now let me discuss other SPT phases protected by this rep D8 symmetry on the lattice. So again, the idea is to do the gauging. So the idea is that we have different rep D8 SPT phases. We want to gauge rep D8 and find different pattern of symmetry breaking of this dihedral group. But doing this gauging in one step is difficult, and we actually don't need to gauge the whole rep D8 to find other SPT phases. In fact, it suffices to only gauge the Z2 times Z2 subgroup. Actually, gauging a single Z2 also works, but here I'm gonna focus on gauging the Z2 times Z2 symmetries. But there are 2 ways to gauge this Z2 times Z2 symmetry. One is the untwisted gauging S that I described, and one is the twisted gauging. So basically, the untwisted gauging actually doesn't change the theory, because the existence of D basically guarantees that the theory is self-dual under the gauging S. So the dual symmetry is also rep D8. So doing untwisted gauging does nothing, sends rep D8 to rep D8 and send SPT phases to themselves. But then there is the operation of twisted gauging. So what's a twisted gauging? So in the continuum, gauging is just correspond to this action on the partition function. You basically make the gauge field dynamical. And there is an operation of T which correspond to attaching SPT, stacking with SPT phases, or adding counter terms. And TST is kind of adding counter terms, doing the gauging, and then adding counter terms, or local counter terms of this, attaching with SPT phases. And on the lattice, so this S up to these prime variables that I introduced before is implemented by this non-invertible operator D. And the operation of stacking with SPT is implemented by this cluster entangler V. So this TST is basically VDV, almost. I will discuss it. So the idea is that if we do this twisted gauging, the rep D8 actually becomes an ordinary Z2 cube symmetry, but with a particular type 3 anomaly. And then different SPT for rep D8 is basically different pattern of symmetry breaking in this Z2 cube. This is the idea. Now let me discuss this twisted gauging on the lattice. So twisted gauging on the lattice, as I said, is correspond to this operation, which is also known as the Kennedy-Tasaki transformation. And this paper has a nice discussion on it. And basically, this is how it kind of acts on local operator. It sends xj to x hat j and sends zz to this zx zeta. And as I mentioned, this is closely related to the operator VDV, modulo this hatted, modulo identifying the variables, the hatted variables with unhatted variables. So now if you apply this TST gauging to the trivial and cluster, you will find these two Hamiltonian. And they are still distinguished because the trivial remains a symmetry preserving phase and the cluster goes to a symmetry breaking phase. This is how do we distinguish them by this TST gauging, twisted gauging. Any question? Okay. So the question is, what is the dual symmetry? So we take the system with a rep D8 symmetry and gauge its Z2 times Z2 subgroup. The question is, what is the dual symmetry that we get? So the claim is that after twisted gauging, we get this Z2 cube dual symmetry, which is generated by these three Z2 operators. So basically, we have the eta hats. I'm just putting hats because in the gauge theory, I want to describe them by hatted variables. So on the product of even sites, odd sites, and we also have the analog of V, but in terms of the hatted variable that I call V hats. So basically, this claim means that starting with any rep D8 symmetric Hamiltonian, if you apply this transformation, the Hamiltonian of the gauge theory always have these three Z2 symmetries, which we call the dual symmetry. And importantly, this symmetry has a type 3 at Hooft anomaly, which is described by this.
Sorry, what are the degrees of these chains? I don't understand this formula. What are you're looking at the anomaly? You're looking at an invertible anomaly theory in 2 dimensions. Are these chains?
Yeah. So we have a 1 plus 1D theory, and this is its anomaly in 2 plus 1D.
I see.
So
okay.
This is a gauge field for this symmetry. This is a gauge field for this symmetry, and this is a gauge field for this symmetry. Because it's kind of A cup, B cup, C is usually sometimes called type 3 Hooft anomaly. One signature is that inserting a defect of for one, the other two symmetries are realized projectively. Thanks for the question. Any other question?
What happened to the operator D after you did this twisted gauging?
So basically, D becomes this invertible operator V with this anomaly.
But what about this coefficient 2? Like at first it acts as 2, but afterwards, why does it become unitary?
So the overall normalization is kind of arbitrary. We just put it such that it has a nice fusion rule. But to say that it becomes V is not kind of a canonical way. The correct statement is that starting with any Hamiltonian, which has the symmetry D and Z2 times Z2, the resulting Hamiltonian has this symmetry, which is generated by these three. But there is no canonical way to say that D is mapped to V. You might want to say that D is mapped to V hat times eta, for example.
Mm-hmm.
So there's no
but it doesn't
one-to-one
like
map.
split
But
into stuff.
Sorry?
Should I think of it as splitting into some like simple object after gauging, or
Yeah, I cannot track the individual ones, but I could say the total rep D8 becomes this Z2 cube.
Mm-hmm.
Yeah, but there is no one mapping between individual ones. Thanks for the question.
A question.
Yes, Julian.
Yeah, Sahand, I'm puzzled by something. So the usual way when we say we have a type 3 Tohu anomaly, these are the anomaly living on the boundary, 1 plus 1D boundary of the 2 plus 1D type 3 SPT, right?
Yes.
In that case, the symmetry realized on the 1 plus 1D will be somehow in the usual will be non-on-site.
Mm-hmm.
And I'm puzzled by the way the first two Z2 symmetry that one select even and all, and the other one The last one seems definitely non-on-site, is that right?
Yes, that's right. So
Yeah,
this
but
you
how
could,
about
you could,
the first,
you could
the
group the
first one?
sites together.
Right,
You could
right,
group
right.
site 1, 2 together, 3, 4 together. So then this acts on site, but then this would
Right.
be not on site.
Okay, so there's only one Z2 among the three copy of Z2. One of them is non-on-site.
That's right. So,
Okay.
so the property of this type tree is that there's only a single Z2 subgroup which is anomalous, which has a pure anomaly, and that's the diagonal subgroup of all of them. I will mention this. Okay. Yeah, thanks.
Okay.
All right.
But
So
then let me just make sure. Then the Z2 also has self anomaly.
So
The V.
the only thing which has a self-anomaly is the diagonal subgroup of all this Z3. So it's eta hat E times eta hat O times V hat.
I see. Okay. Okay, thanks.
Yeah, thank you. That's related to the Levin group model. All right. So one observation is that all rep-D8 SPT phases are in the same Z2 times Z2 SPT phase. This is because, all of them are self-dual under S gauging. And that would mean that all of them after the TST gauging goes to a trivial phase. So because of that, all of them are in the same Z2 times Z2 SPT phase. The other observation is that because of this, after twisted gauging, the dual Z2 times Z2 must be broken. And these two observations will help us to list the possibility for the different pattern of symmetry breaking in this Z2 cube if we start with some rep-D8 SPT phase. So to summarize it, is that if we start with a rep-D8 SPT phase and perform twisted gauging, only a single Z2 subgroup of this Z2 cube symmetry must be preserved, while this one has to be definitely spontaneously broken. This is coming from the fact that the original symmetry was invariant under, the original state was invariant under D and hence under S gauging. So a priori, there are 4 possible symmetry breaking patterns in the gauge theory. One is that Z2V is broken, Z2V is unbroken, or the diagonal Z2 symmetry here is unbroken, and we have these 4 possibilities because there's a single Z2 subgroup which is preserved, but is not a subgroup of Z2 even times Z2 odd hats. All right. But the last one is actually impossible because as I mentioned, this symmetry it has a pure anomaly. So there is no way to have a phase or some gapped symmetric state that preserves this symmetry. And the first possibility is just basically realized by the cluster SPT, because if you look at this Hamiltonian, this preserves the Z2 hat V. And I will actually give you lattice realization for phases that realize the option 2 and 3. That will only preserve these subgroups. All right, so now let me tell you how to realize the phase which only realizes this subgroup. So this is a proposal. So we have to take a chain. So I first give you the Hamiltonian in the gauge theory, and then do the gauging back to give you the Hamiltonian of the original SPT. So here we take the number of sites to be a multiple of 4, and this is a proposal for a phase that only preserves the diagonal subgroup of Z2 hat V times Z2 hat even. So to see this, first note that this is an exactly solvable model. All the terms commute with each other, and basically could diagonalize all of them simultaneously. So this term here is not important for finding the ground state, because basically this term, if you want to minimize all of these terms, so you have to set this to be -1, and this term is a product of 2 such terms. So this is +1. So basically this term doesn't matter. So you could find a ground state by setting z hat to 1 and z hat to -1 and y hat to +1. And you will see that there are 4 ground state and 2 order parameters. And these 2 order parameters are invariant under this diagonal Z2 subgroups. So then hence this phase, breaks spontaneously this symmetry down to this Z2 subgroup. So now to find the Hamiltonian for the rep-D8 SPT phases, basically we have to gauge this Z2 times Z2 symmetry back. and do the reverse of the Kennedy-Tasaki transformation, or this TSD gauging. And we will find this Hamiltonian that we call H odd. And its ground state has a simple form, and basically its ground state is stabilized and satisfy these conditions. So we have L conditions, and hence uniquely that the ground state is determined. So this is some condition for even site, and this is some condition for every odd site. So the proposal is that this Hamiltonian is in a different rep-D8 SPT phase than the cluster state, than the cluster Hamiltonian. Is there any question about this claim? Okay. And also we could, by conjugating this Hamiltonian with translation, we could also, provide an SPT for the other phase, which instead of preserving this, preserve Z2V times Z2 odd. This is just conjugation by translation. And at the end, the claim is that we find these three SPT states, which have this formula. So we could start with some product state and apply some quantum gates to construct them, some quantum circuit. And again, as I said before, all these rep-D8 SPT phases are in the same Z2 times Z2 SPT phase. This is basically because, taking any of these states, let's say odd and cluster state, they can be related by this quantum circuit. So you could take, they're related by this exponential, and now we could tune this parameter T from 0 to 1 smoothly. So these two states are smoothly connected. And unless the cluster entangler, each individual term here is Z2 times Z2 symmetric. So this odd state can be smoothly connected to the cluster state while preserving Z2 times Z2. So they have the same Z2 SPT, Z2 times Z2 SPTs, but they are in different rep-D8 SPT phases because this unitary symmetry breaks rep-D8, even though the initial and final states are rep-D8 symmetric.
Question. So do these three phases realize the three fiber functors of rep-D8?
That's true. That's true. Yeah. So I will make some connection about the classification in the continuum. Yeah. So in the continuum, they are classified by some fiber functors. Here I'm just giving its lattice, their lattice realizations.
Yeah. Thanks.
Yeah. Thanks for the question. Any other question? Okay. So now let me discuss the edge modes between these SPT phases. So like the cluster model, we could again take a chain of L sites and divide it into two pieces. So from site 1 to L, we could insert the cluster state, and from site L to site 1, we put the other phases, odd states. So this would be the Hamiltonian for this interface system. And again, the idea is to find some projective algebra at the edges. So you could show that this Hamiltonian has 4 ground state again, and we want to show that there is a doubly degenerate edge mode at each of the two left and right interfaces. But the way that the symmetry localized on the two interfaces is a bit different from ordinary invertible symmetries. So for eta odd, it basically localizes as the product of two terms on the left interface and right interface. But for the non-invertible symmetry operator, actually it localizes in the product of two terms, but we have sum of two such terms. So this is a distinction from the ordinary case. And for this case, for the edge modes between cluster and odd, the eta even symmetry kind of act trivially on all the edge modes. So this size is in the ground space of this interface model, interface system. Okay, so now let me tell you what the projective algebra is. So basically, as I mentioned, on these interface states, these localized this way is the sum of two terms, and these are some explicit relations for this DL left and DL right. And from this expression, you could see that there is actually this projective algebra, which tells you that these local factors of D are charged under the Z2 odd symmetry. So there are two of them, 1 and 2, and you get the same phase. So eta even kind of acts you know, if you look at this, this is, so here I'm taking L to be even and also this L to be even. So this has a charge under Z2 odd, but it doesn't have a charge under Z2 even. And we get these projective phases. The idea is that these projective phases protects the edge modes at the two interfaces, like the ordinary symmetries. Any question? Okay, so now let me mention that these three SPT phases, this is closely related to these projective phases, can be also distinguished by the symmetry charges, the D defect. So this is something that's going to appear in the longer paper. So basically, the three non-invertible SPT phases are distinguished by the Z2 even times Z2 odd charge of the D defect. And they have these quantum numbers. So what do I mean here? So basically, we could take the Hamiltonian of each of these model and insert a single D defect. So we put kind of a D-twisted boundary condition for this system. And then we look at the action of the Z2 even and Z2 odd on the ground state of this system. And we see that on this system, one of these three Z2 symmetries is going to have odd charge. So it means that the defect of D has a charge under each of these three symmetries. And that also explains the terminology of why we are calling this SPT state the odd state, because it has a charge under the Z2 odd. And the even SPT state has a charge under the Z2 even one, and the cluster has a charge under the diagonal one. And another comment is that the three SPT phases are related by the triality automorphism of Z2 times Z2. Okay.
Sorry, can I ask, in the D-twisted Hilbert space, how many ground states are there?
So there are two ground states,
yeah.
But for both of them, this is you get a minus sign.
Oh, I see. Okay, thanks.
Yeah, thank you. This is basically because both of this is related to the fact that both D1 and D2 have the same charge. This number 2 is related to this 2. Yeah. Any other question? Okay, so now let me also make some comment about this entangler that I mentioned. So the claim here is that for non-invertible SPT phases, there is no symmetric entangler that relates two different SPT states together. So more precisely, we are claiming that there is no rep-D8 symmetric unitary operator U such that it maps different SPT states together. Let's say there is no such an entangler that maps the cluster state to the odd state. So the idea of the proof is simple. Basically, we want to show that the existence of an entangler U, which by definition will satisfy this 4 property. So these 3 equations basically correspond that is a statement that this commutes with the symmetry is a symmetric entangler. And this is just this equation. So we want to show that these 4 equations, the existence of U satisfying these 4 equations implies the existence of U hat in the TST gauge theory after twisted gauging that commutes with the dual symmetries and map the cluster hat to odd hats, where these 2 states are the symmetric ground state of the Hamiltonian of the gauge theory. So the idea here is that we have this U, and basically we want to look at we can hypothetically think of U as a symmetry of our system. And then we are doing the gauging, and this U hat would be the quantum symmetry or the dual symmetry after gauging. And because this commutes with this, one could show that U hat still remains a unitary symmetry and commutes with the dual symmetries. But this fact is impossible. It's because the cluster hat and odd hat have different pattern of symmetry breaking. So they have different order parameters which have different charges under these dual symmetries. So it would be impossible to map them with the U hat which preserve the symmetry. And because we have a contradiction here, so it means that U cannot exist. But that's the idea of the proof. Unlike the case of ordinary symmetries, where such an entangler is usually exists. There is no proof for it, but usually exists. Okay, so now let me summarize about these SPT indicators, SPT indicators for the case of Z2 times Z2 and RepD8. So we discussed 4 different indicators. One was the projective algebra that, for the Z2 times Z2 case was just this minus sign at the interfaces. And we also have this projective algebra in these cases. And the other one was the spontaneous symmetry breaking, defects, and the entangler. So now let me conclude with some comments and some conjectures about the distinction between invertible SPTs and non-invertible SPTs. So the first condition is that there is no stacking between non-invertible SPTs, or basically theories with non-invertible symmetries. Having 2 theories with the same non-invertible symmetries, there is no way to stack them such that, or take their tensor product such that the resulting theory have the same non-invertible symmetry. So in particular, that would tell us that there is no clear way of defining the notion of invertible TQFT equipped with the non-invertible symmetries. So the non-invertible symmetry SPTs are not described by invertible TQFTs, unlike the usual case. The other thing is that the existence of the fact that there is no symmetric entangler relating different non-invertible SPTs, it suggests the following conjectures. So the first one is that the classification of non-invertible SPTs is not relative. Note that in the continuum, the classification of usual SPTs is relative. Because what is really meaningful at long distances is the relative counterterm between 2 theories. Because if you have the product state or the cluster state, there is a unitary operator, which is basically like a change of basis that sends one state to other states. So at long distances, if you don't specify your regularization, you cannot distinguish them. Only the relative SPT phase between them are meaningful at long distances. So and because of this, it suggests that the non-invertible SPTs even have a different pattern of long-range entanglements protected by non-invertible symmetries, and not only short-range entanglements. And the last one, it suggests that there is no corresponding anomalous symmetry in one lower dimension for these non-invertible SPTs, because the procedure to do this bulk boundary correspondence for ordinary symmetries uses this symmetric entangler, which was explained in the paper by Elsa and Nayak. So if you have this symmetric entangler, starting with the SPT states, you could construct an anomalous symmetry on the boundary. But if you don't have this symmetric entangler, at least I don't know how to construct an anomalous symmetry in one lower dimension. And so with this, let me end my talk. Thank you for your attention.
Great, thanks very much for this really clear talk. Other questions? I actually have a question to start with. So you were saying that for rep Q8 and H8, there are these, right, which are sort of related, TY, Z2, Z2 with different bi-character and for being sure. Do you know how to construct lattice models that construct the SPTs for those?
We haven't thought about those examples.
Because you start with Z2, Z2, and then you gauge essentially, right? So it's sort of like constructing the rep D8 in some way from a Z2, Z2 symmetric.
Right. Oh, right.
And the question is, could you now include the slightly more refined data about the associators?
Okay. Right. I think this is done in the paper by Nat. So for Q8 and H8, they admit basically a single fiber functor in the continuum. So you expect only a single SPT for them. And so there is a MPO.
In the continuum, I understand. I meant the lattice model.
Yes. So there is an MPO presentation of these operators. That is, for example, is discussed in the previous paper, but I got also Nat also discussed in some of the same.
That's true. Yeah. Thanks. Abi.
Hi. So could you tell me if the classification, do you expect the classification of non-invertible SPTs to have a group structure at all?
Yeah, I don't know, because it is related exactly to this comment that there is no stacking. So it's not clear how to stack them and define a group structure between.
But that does not necessarily mean that there is no group structure, because the classification of SET phases has a group structure, even though there's no stacking interpretation.
Yeah. For non-invertible symmetries, is not clear. Yeah, I think there is no group operation. Yeah, thanks.
I actually
guess
had to, I will ask another question if they're not, and I had to miss a little bit because we had a fire alarm here halfway through. But maybe you said this. Did you talk about the order parameters for these 3 different SPTs? It's a distinction. Like in one case, in the cluster state, you did talk about it. What about these other odd and even ones?
Yeah, so I did not talk about it because the order parameter would be more complicated because
Yes.
the fact that this is sum of 2 terms.
Yeah.
So the order parameters wouldn't be a single string operator, but it would be a sum of 2 string operators.
Yes. So some generalized charge type construct. Not.
Hi, thanks for the very nice talk. So you mentioned that there's a unitary, so you had some unitary connecting the cluster and odd, right? Like, yeah, if I just took the difference of that too, that would give me a unitary. So what is the catch here in this example?
Okay, that the total symmetry here is not rep D8 symmetric, the total one, not the individual gates. Even the total one doesn't commute with D.
Okay, so if I mapped it to another, so if I conjugated everything, I would get another operator, which would not be D. And so I conjugate this unitary with D, I wouldn't get D back anymore.
Exactly, yeah.
But then in the new state, D would also still be a symmetry, in addition to this others symmetry.
So in this case, we start with a cluster, we act with this unitary, and we still get a D-symmetric state. But if you take this unitary and act on a generic D-symmetric state, you might not get a D-symmetric state because this total thing doesn't commute with D. It was a coincidence that here it maps 2 D-symmetric states to each other. Whereas for the cluster entangler V, it always, sends a Z2 times symmetric state to Z2 symmetric states. So you could interpret the cluster entangler as the unitary that implements the operation of stacking with SPT. But there wouldn't be such a thing that, would implement the operation of stacking with non-invertible SPTs.
Okay, thanks. I actually had another curious comment, which was if you got rid of D, but instead impose time reversal, I think these states are different phases. So I was curious whether there's some relation with that.
Oh, you mean further these 3
So just restrict to Z2 times Z2, but then I impose time reversal on top of this.
Instead of D, you want to impose time reversal.
Yeah, then I think these become distinct SPT.
Yeah,
so
I have
curious if there's a potential relation, but yeah.
I see. How many so you also find 3 SPTs for time reversal?
There's the pure time reversal one, but I ignore it. There's sort of there's a mix like Z2 and Z2 time reversal, like odd time reversal, even time reversal, and then there's the one where it doesn't have time reversal.
I see. Yeah, thanks for this comment. Yeah, I'll think about it.
Okay, Jing Yang.
Hi, Sahand. Nice talk.
Hi.
Yeah, so I have one question on the stacking of the non-invertible SPT. So if I understand correctly, is because of for the non-trivial fusion rule, usually you cannot find the closed subfusion algebra of that, right? I mean, diagonally.
Yeah, that's true.
So I guess my question is, if there is some, I don't know, some special kind of fusion category which I can indeed find diagonal closed algebra, is it possible to build SPT stacking, or is just always not possible?
Okay, I think the closeness is not sufficient. I think what you want to have is the following, that you have 2 non-invertible operator, let's say D. So take D, and let's say you have 2 theories. So the diagonal symmetry in the tensor product theory would be D tensor D. The idea is that D tensor D satisfy a different fusion. But one thing that is kind of a no-go for this is that D tensor, if D is non-invertible, its quantum dimension is not equal to 1. So it's equal to D, like lowercase d. Then D tensor D's quantum dimension would be D squared. So it would be definitely a different kind of symmetry. So even if it closes under fusion, it would be a different fusion algebra and different fusion category. So the diagonal theory, the tensor product theory does not have any canonical fusion category of the same type.
I see. Okay, thanks.
Yeah, thank you for the question.
Okay, are there any other questions? Let's actually thank Sahand again for the super nice talk, and I'll stop the recording.